Yay! Let's do some calculus. This makes me so happy now because you get to learn things now and connect ideas, and you know enough now that everything is interwoven, and I'm just so excited. Let's do this. So up here it's talking about interpretations and applications of the derivative and definite integral. So we're going to be going back and forth from the derivative to the definite integral. So if I take the derivative, remember this just seems like the derivative of an amount. We get an amount at the rate at which the amount is changing. So if I take the derivative of bunnies, for instance, the number of bunnies, I get some bunnies per unit of time. Like I would get like bunnies per hour, per minute, or whatever. And you might be like, what are you talking about? But this could be like the rate. If we talk about the number of bunnies, this could be the rate the bunnies are being born or something like that. Any amount, if I take the derivative, I can get the rate at which that amount is changing. So for example, if water is being drained from a swimming pool, R of T represents the amount of water. So this is the amount, and it's measured in cubic feet. So that seems important. That it's in a swimming pool at any given time, measured in hours. So we're given the time. I just made this up. I made the amount, I made the time up, but you'll be given it in a problem. Then R prime of T will represent the rate at which the amount of the water is changing. So if you take the derivative of some amount of water, you get the rate at which it's changing. If we're talking about the units, this is the change in y over the change in x, or the change in RT in this problem over the change in x. So this is going to be the change. RT was measured in cubic feet. dx would be the change in time in this one if I take the derivative. So in this one, I'm going to say hours. So cubic feet per, I should just say 1 hour. It seems weird to say more. So cubic feet per hour. So if I go backwards and I take an integral of the rate, I get the amount of change. So let's think about this. This helps explain. So do you remember how we just talked about the fundamental theorem of calculus? And we could say the antiderivative of r prime and antiderivative is r of b minus r of a. Well, if we think about this, if this is the rate at which water is being drained from a swimming pool, this would be the change in the amount of water. So this is always the amount of change in whatever this was given in. So I'm going to say cubic feet in this one of water from time A to B. So the derivative gives you the rate. If I take an integral, because of fundamental theorem of calculus, where I can say the antiderivative f of b minus f of a, or in this case, r of b minus r of a, this is the amount of change in cubic feet of water. It's very exciting. It's all kind of coming together. And this one, the table is given by the velocity of a particle. Okay, so velocity, that's exciting, where t is measured in minutes. So we've got time in minutes, we've got velocity here. This asks me to approximate the value of the particle 0 to 30 of v of t using a midpoint Riemann sum. So what this is asking, anytime you see something like this, we want the area under the curve of v of t. I can see it matches. This one, even if you just kind of went on autopilot here and you just said, oh, I need to do a midpoint Riemann sum, that's what we're doing. Like if you take it and you make a bunch of rectangles or whatever, that's what's going to happen here. It's just anytime you have an integral, this always would have to match up. If you're doing the area under the curve, whether it's the Riemann sum or otherwise, these would have to match up. And they do. So a midpoint Riemann sum, this one actually doesn't say how many units, but because I know it's midpoint, it usually would say how many subintervals. But I'm going to break this into 3. I could have put this at the top too. Like I'm just saying there's 3 different rectangles. Because it's a midpoint Riemann sum, so I'm going to circle whenever I do my height, I'm going to find it by the midpoint. So I would take the distance from here to here, so my base would be between 0 and 10, and I get 10. My height is going to be whatever this midpoint is, so this would be f of 5, or in this case v of 5, and I would get 1.6. Then I go from 10 to 20, and I can see I have a distance of 10. My midpoint in this one would be the function value or velocity at 15, which is 3.1, plus over here 20 to 30, again 10. This is nice, they're all the same length. Doesn't have to be, but this one's fun that it is. Midpoint, so I'm using the midpoint value for the function value, 1.6. If I multiply all these things together, you could do 1.6 plus 3.1 plus 1.6 all times 10, but you should get, I'm going to skip ahead to the 63. Oop, I almost put the units right away. Ignore that for a second. So I have 63. Let's think about what the units would be. If I have an integral of v of t, and I'm integrating v of t, what this is equal to, according to the fundamental theorem of calculus, 0 to 30 of v of t dt is equal to the area under the curve of v of t, but also we can say p of 30 minus p of 0. P is position. Position would just be measured in feet. You can also think of it like this. If you have a graph of v of t, I'm not going to use these exact numbers, I'm just going to say this is v of t, and I can see that the y-axis is measured in feet per minute, and the x-axis is measured in minutes. If we have any curve, and I find the area under the curve from, let's say, some a to b, let's think about what units would be on here. I would take the base times the height, or I could say the height times the base. So I could say minutes times feet per minute. You take an area, minute times feet per minute, these minutes are going to cancel out and you're just left with feet. So if I did the area under the curve and I'm multiplying the units, I can see that it'd still be left in feet. Or if you do the fundamental theorem of calculus, the antiderivative of velocity and antiderivative is position. Position at 30 minus position at 0. This is helpful in thinking about units. This is also helpful in thinking about units. But this is helpful to think about using correct units of measure, explain what this value represents. Since I'm doing p of 30 minus p of 0, that's my position at 30 minus my position at 0. What I get here, the 63, is going to be the amount of change in position. So I'm going to say from 0 to 30, what units was I using? Minutes. The particle moves, and I'm going to say, you can say the particle changes position, or position changes by 63 feet, or you can say moves a net distance, because we talked about this before. You can't say total distance because it could be moving back and forth during that time, but it moves a net distance of 63 feet. Or you can say, if you wanted to be safe and you didn't want to remember the net distance part, even though that's a good thing to remember anyway, you could say from 0 to 30 minutes the amount of change in particles' position is 63 feet. So this one or this one. You don't have to say both. I'm just giving you some options here. Okay, let's do another one then. This one says, what is the value of this integral 5 to 25 a of t dt? Okay, so I'm saying the integral from 5 to 25 of a of t. So should I do the area under the curve? And I look up here and I'm like, oh no, they don't match, which means that I can't do a Riemann sum even to approximate this. So I have to be thinking a little bit more. Okay, this integral from 5 to 25, it would equal the area under the curve of a of t from 5 to 25, but we don't have a of t graphed. So the other thing that it can equal, think about the fundamental theorem of calculus, what would that be? An antiderivative of a of t. What's the antiderivative of acceleration? Velocity You know, when we did the f of b minus f of a, according to the fundamental theorem of calculus, that's what's going on here. So if I'm thinking about this, v of 25 minus v of 5, I can just go up here and I can say, oh, that's 1.6. Really, I know this is feet per minute, minus v of 5 is 1.6 feet per minute. So if you subtract them, I still get 0 feet per minute. What does that mean? Well, this was the velocity at 25 minus the velocity of 0. So I'm going to say between 0 and, or I'm sorry, 5 and 25 minutes, the change, or I can say the amount of change of velocity, just so you can use this for everything, change in velocity is 0 feet per minute. Ta-da! We just connected derivatives and integrals. So exciting. Let's do more. So on the next page, now we get into problems. So in this one, we've got the temperature of water in a tub. So these are really good free response questions if you haven't noticed by just even the setup of this. So the temperature of water in a tub is modeled by strictly increasing. This means that this function will never have a derivative of 0. It's always going to be a positive derivative, strictly increasing. That's what this means. So the derivative will not be 0. It'll just be positive, 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 and never stop at 0 for a second. Twice differentiable. That's nice. So lots of theorems can be used here if needed. W of t is measured in degrees Fahrenheit. T is measured in minutes. So we're given W of t degrees Fahrenheit. Okay, I'm all set up. Got this. Using the data in the table, estimate W prime of 12. So you have so many tools to use now. How do we estimate the slope of a tangent? We find the slope of the secant. So W prime of 12 is approximately, I'm going to go between 9 and 15. So I'm going to pick a value here and here. And I'm going to say y2 minus y1, or in this case, W of 15 minus W of 9. And it's really important to write this just because whenever you're justifying, if you mess something up, it's good to have this part. And even if you don't, it's also good to have it because there are different ways people approximate this. 15 minus 9. So this would be 67.9 minus 61.8. 15 minus 9 is 6. And then you can keep it like this if you want. So once you get the 6.1 over 6, you can keep it like that. If you change it, you can either write, if I truncate, it goes like this. If I round it, it goes like this. So I started to write degrees, but that's actually not my unit. Keep thinking about this. What would it be? Use the work that you've done to help you. So do you see the numerator? This is W. W is measured in degrees Fahrenheit. The denominator, 15 minus 9, was minutes. And that's nice because W prime of 12 is a rate. That's what we want it to be. Same thing down here. You don't have to rate both of them. You could have just had this or this or this. So when it says using correct units, we've got those. Interpret the meaning. Remember that the derivative is the slope of a tangent. So even though we're estimating that, this is what it means. We're finding approximately what the slope of the tangent is. So I'm going to say at t equals 12 minutes, because the derivative always happens at a moment, the rate, the water temperature is changing. Water temp is changing. And this is where it's important, is approximately, because we estimated using the slope of the secant line, 1.016 degrees Fahrenheit per minute. I said at a particular moment, at t equals 12 minutes, I said that this was the rate the water temperature is changing. and then I gave my answer with correct units. We did it! Let's go on to another one. Use the data in the table to evaluate this. Okay, so let's think about this. I could do the area under the curve if I have W prime of t. I don't. They don't match, so I can't do it that way. The next thing I can do is I can think, okay, what about the fundamental theorem of calculus? If I say 0 to 20, W prime of t dt, that would be equal to f of b minus f of a, or in this case, w of 20 minus w of 0. That's going to help us to interpret the meaning of this integral. W of 20 is 71.0. W of 0, sorry, I'm going up here. W of 20, 71.0. W of 0, subtract those. W and W, this whole thing was measured in degrees Fahrenheit. Remember that an integral is always an amount of change over some given amount of time. So I'm going to say from 0 to 20 minutes, the amount of change. It's really helpful to get in that habit of writing the amount of change, just like before we wrote the rate when we were talking about derivative. The amount of change of the water temperature was 16 degrees Fahrenheit. I put correct units. I have my time on here. I'm making sure to talk about what this is the amount of change in water temperature. I'm good. Now it says from 20 to 25. Not on here. So 20 to 25 beyond this. The function w that models the water temperature has a first derivative given by this. So this is only 20 to 25. Based on this model, what is the temperature of the water at time t equals 25? Okay, so let's think about this. Is there anything that I know? Well, if I want the temperature and all I've got is a derivative, I need to start there. So I need to think, okay, what if I integrate? Because I know the temperature at 20 is 71, so I can figure out what the temperature is at 25. I also am only given a derivative, so the only way I get back to temperature is by integrating. Remember to put, whenever you're writing this, really important to put w prime t dt, because this is going to be the, when we were drawing all those rectangles, remember this is the height, this would be like the width, the change in whatever the x value is, or in this case t. Okay, to do this you might be like, okay, well I know this is equal to w of 25 minus w of 0. But the problem is, I don't know w of 25. Oh, I shouldn't have said 0 right here. I should have said 20, because this is 20 to 25. I do know the water temperature at 20 is 71. It's given right here. Okay, this one's still a problem though. What could that be? This is where it is totally acceptable to use your calculator. So I'm going to go into my calculator and I'm going to push math, and I'm going to go down to number 9. And this integral, I'm going to write it exactly like it is right here, 20 to 25. And make sure that I put in exactly like it is over here, except I can switch in x's. So I'm going to do 0.4 square root of x cosine 0.06x, and then dx. This just gives me the change from 20 to 25 in the water temperature. So I'm going to write over here 2.043154.6, and I think that would be enough to make sure I have at least 3 places after the decimal. Oh, sorry. So you don't round this to 3 places until your final answer. This one's not that big a deal because all I'm going to do is add 71 to this. W of 25 is going to be 73.6. 0.043. Here I can take the 3 places after decimal. Don't forget degrees Fahrenheit. Did it! Okay, so I feel like I'm going to change things up a little bit, but that was 170, which we did 178 and 179. I'm going to actually give this time to sink in, and the next one we're going to have 2 more to do at the same time. Okay, thanks for being awesome. I appreciate you. I think you're awesome, and yeah, I'm super glad I get to teach you. Have a great rest of the day. Bye.